This is AS Module 2, a paper from January 07, and it's question 3, and this question focuses on lenses. Sketch a diagram to show the location of the optical centre of a diverging lens. Well, we should start initially with the diverging lens. It's always narrower in the centre than it is at the edges, so we draw the diverging lens. We then should draw in our principal axis, which goes through the centre of the lens. And the optical centre, if we draw another dotted line through the lens vertically, the optical centre is right in the very centre with the principal axis and the vertical centre across. So this is C, because they call it the optical centre of C, so you should label it as C or optical centre. And make sure that it's on the principal axis. Part 2. Figure 3.1, which is down below here, shows an object OA on the principal axis of a lens. This lens produces an image of this object which is virtual, upright and diminished. State the type of lens which must be used. Well, we can use a converging lens or a diverging lens to give us a virtual image. And in both cases, the virtual image will be upright. The key term here is the diminished. If we use a converging lens to produce a virtual image, it's always enlarged. Therefore, it's a diverging lens. And a diverging lens always produces a virtual, upright and diminished image. In the second part of this part 2, draw the lens on figure 3.1. So we first of all have to draw the lens. Label its principle of foci on the principal axis. So foci is the plural of focus, therefore we're expecting 2 points labelled. And on figure 3.1, complete the ray diagram to show how this image is formed and label it IM. So we're looking for an image that we will label IM and show a suitable position of the eye to view the image. So there are several different parts to this question. And the first one is to draw the lens. So using our ruler, make sure the lens is at right angles, 90 degrees to the principal axis. And we can draw this really at any position. Now, it's a diverging lens, we said, so we must show the arrows pointing towards the centre because it's a diverging lens. And if we want to produce an image which is diminished, then we should place the principal focus closer between the object and the lens. So if I mark it at 2 centimetres out, you could use any value that you choose. The other principal focus must be on the right hand side at the same distance, and we label that F. So checking the question, we've drawn the lens and we've labelled the principal foci. Now we're going to complete the ray diagram to show how the image is formed, and we're going to label it IM. The first ray for a diverging lens, we draw through the optical centre and it passes straight through undeviated in the optical centre. That's simply a line presently. We must put an arrow on it to make it a ray. The second ray that we can draw travels parallel to the principal axis, and when it meets the lens it's diverged, as if from the principal focus on the left hand side of the lens. So we draw in our ray diverged, and we must continue this ray backwards towards the principal focus to show where it apparently came from. And because that's virtual, we must use a dotted line for that. So put on our arrows on the ray before we forget. And the point where the virtual ray and the actual ray meet is where your image is formed. And as we can see, it is upright and diminished. and we label it as IM. M. So we have now completed the ray diagram. We've shown how the image is formed and labelled at IM. The final thing that we need to do is show a suitable position of the eye. And the eye is anywhere over on the right hand side in the direction that the rays are pointing. The marks for that question, according to the mark scheme, you would get 1 mark for having the ray through the centre drawn correctly, 1 mark for locating F and drawing the ray through it. So those two aspects are combined, that you have F and you have the ray diverging from it. A mark for the image, which is labelled and located correctly, and a 4th mark for drawing the position of the eye. Had you done that question and forgotten the arrows, you would have lost a mark. Or had your virtual ray not been dashed, you would also have lost a mark. So it's very easy to gain marks in that question once you learn the diagram, but it's also very easy to lose them through carelessness. Moving on to part B of that question then. An illuminated object is placed a fixed distance from a white wall in a room. A converging lens is used to form a real image of the illuminated object on the wall. The lens is to be moved so that the image of the object is to be the maximum size possible. So we have a converging lens, and it's real because we can form it in the wall. The wall acts as a screen. And the question asks us to describe where the lens would be placed relative to the object to obtain this outcome of the maximum size possible. Well, to get the maximum size, it's largest whenever the object is placed between F and 2F, and the closer you get to the focal point of F, the larger the object gets. So the object is just outside the focal length, as close as it possibly can be to the principal focus, but just outside it. Of course, if it's placed at the principal focus, the rays will never converge, and you get the use of that as a spotlight. Now, a long description for the next part of the question. In a camera, the film acts as a screen to receive real images of distant objects formed by the converging lens of the camera. An electromechanical system in an autofocus camera moves the lens towards or away from the film inside the camera so as to produce a sharp image of any required distant object. The focal length of this lens is 55mm. That's our first useful piece of information for a calculation, and that's F. A sharp image is formed by such a camera when the object to be photographed is 1.5 metres away from the lens. So this is U, the object distance. The object is then moved to a new position 9.5 metres from the lens. Calculate the distance the autofocus system must move the lens from the first position of the object to the second position to produce a sharp image in both cases. So if we call the 1.5 metres U1, the 9.5 is U2, of course F is always constant. The equation we need to use for this calculation is the lens law. So write that down first. And generally, there's a mark for that in any calculation. If we consider the first position and substitute into the equation. Now, looking at the answer box, the answer is in millimetres. The focal length we're given is in millimetres, but the object distance is in metres. We have to be consistent with our units, therefore I'm going to convert the object distance from metres into millimetres, and we're going to substitute into the equation. So the focal length is 55 millimetres, U is 1500 millimetres plus 1 over V. When we rearrange that and calculate it, in this case, this is V1, is 57.09 millimetres. And that sounds logical, to have 57 millimetres inside a camera. Had we had anything too large here, we would have to think about recalculating, because you must bear in mind the size of the camera. In the second position then, the focal length is still 55. The object distance this time is 9.5 metres, which is 9,500 millimetres, plus 1 over V2. When we rearrange and calculate that, we find that V2 is 55.32 millimetres. Now the question asks you to calculate the distance it must move. So we're looking from the difference between the original position and the second position. So the distance is equal to V1 minus V2, which is 57.09 minus 55.32, which gives you 1.77 millimetres. So in terms of the marks for that question then, in the mark scheme they gave 1 mark for the equation, 1 mark for calculating the first image distance, 1 mark for calculating the second image distance, and then the final mark for the answer, which is the difference between them. So to summarise in that question, we were asked to draw and identify the optical centre of a diverging lens. We were then asked about an application of a lens, and we had to draw the ray diagram for the formation of an image using a diverging lens. Part B then moved on to a different application where we were using a converging lens, and we had to describe where the lens should be placed relative to the object to ensure that you get a maximum size of image. And then we did a calculation involving the lens law, and we found the image distance for the first object position, the second object position, and then found the difference in them.